The Last Lab, Faraday's Law by me, Nathan Tyler. The purpose of this lab is to visualize the effects of Faraday's Law by dropping a magnet through an aluminum foil tube. We will then compare these results to a Python model we made later on. For this lab, you will need a smartphone to record the experiment, a bar magnet to drop through the roll of aluminum foil, and a tape measure to take all the measurements of the aluminum foil. For some of the physics principles we'll be using in this lab, first is Biot-Savart's law shown in the top right. The next is Faraday's law, which is in the middle. Then we have the force of a dipole on a loop in the bottom left, and finally the flux in the bottom right corner. Now for the experiment. First, we must mark the north end of the magnet using the magnetometer app on our iPhones. Next, we must hold the aluminum tube vertically in the frame and not sitting on the ground so we can see the magnet come out the bottom of the tube. With the tube held, we must record the magnet falling through the tube so that way we can time it. And after we repeat the experiment 5 times, we must take the average. Now for a few questions. Why can't we use a ferrous tube like a steel pipe? Ferrous means containing iron, which is magnetic, so it would attract and hold the magnet instead of letting it fall. What happens to the magnet? The magnetic field created by the tube and the magnet creates a magnetic force that points opposite of gravity, which slows the fall of the magnet. How does this compare to the magnet falling in free space? In free space, the magnet would accelerate at the speed of gravity with no resistance, compared to in the tube where it has the resistance of the magnetic force. Now for my measurements. The length of my tube of aluminum foil was 0.4 meters. The width of my aluminum foil was 0.02 meters. The mass of my magnet was 0.014 kilograms. The inside radius of the tube was 0.025 meters, and the average time of the magnet falling through the tube was 2.45 seconds. Next, I took all the values of the aluminum foil that I measured on the previous lab and inserted them into my code on the left highlighted in the red box. Next, I took the values of my magnet, the mass, and inserted it there. And then I took the mu value of my magnet from lab 3 and inserted it into the code on the right side inside the red box. This is my code's output. As shown on the graph on the bottom right in the velocity versus time graph, the magnet speeds up till reaching the tube, then decelerates to its terminal velocity inside the tube, and is kept at this speed until exiting tube, shown by an increase of speed again at the right. My experimental time of the lab was 2.45 seconds, and the computational model was 2.137 seconds. So overall, I think the model was really accurate. Intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which current counterclockwise? How do you know? Since the change in flux was increasing in the negative y direction because the magnet was facing down, the blue current represents counterclockwise rotation opposite the flux. What happens to the dynamics of the system when you flip the magnet around? The current would also change. What's the total time in tube of your real-world system compared to that of your computational system? How might the computational system be made more accurate? My experimental time was slightly higher than the computational system. This could be anything from inaccurate measuring or unsmooth release of the magnet. Overall, though, I believe the computational system was pretty accurate. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The bar magnet gains speed till reaching the tube, then the speed slows and becomes constant till exiting the tube. So while the magnet was in the tube, the forces on the magnet would be equal to 0 since the magnet was no longer accelerating. What if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity of the conductors approached zero, the induced current would increase, therefore increasing the magnetic force and slowing down the magnet. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The magnet would fall faster because the number of complete rings would be lower, which would decrease the induced current generated. Thank you for watching my last lab. Have a great day.